here. I just want to check, make sure the live stream is working. Okay. Yeah, we're continuing with networking, and we are working on the receive portion of networking, and we've made some good progress. And so last time we were working on exercise 10. And exercise 10 involves setting up and configuring the E1000 to initialize receiving. A little bit later on in exercise 11, we're going to actually receive data, but for the moment, we were just working on initializing the NIC. And we finally got that working last time. I mean, it was kind of actually always working, but it was just kind of challenging to configure QEMU correctly to print out this confirmation logging message that things were actually working. So we got that working. I'm going to do my usual test in the chat just to make sure the chat widget is working. Test Twitch. All right, welcome to everyone joining the stream. Yeah, so I also did a bit of reading about the E1000 network card over the week, and I actually have a lot more clarity around how it works coming into this. So I'm pretty optimistic we'll be able to make some good progress. Finally kind of just learning about how these transmit queues, like how these queues work. There's a transmit queue and a receive queue. And the way they work is a little bit asymmetric, actually, and that is something that took me a little bit of time to understand. So we'll get to apply this knowledge a little bit later on when we actually write the function that receives data from the NIC and actively uses the receive ring buffer. Afnan, what's up, dude? Thank you for the test 1. How are you doing this week? I hope you're having a good one. And I hope you figured out you were working on your own OS and you had a bunch of boot issues, if I was recalling correctly. It's very weird that your computer wasn't recognizing the USB drive, even though it did for other ones. So what's up, everyone? What's up, Kundan? What's up, Izalde? Got another test 1 in the house also. Very cool. Very cool. Thank you for the test 1s. So let's get into it. Let's ease into it. Let's first just get back into the code a bit. Things are compiling. So I was having, yeah, this is a, whoa, okay. Let me just reproduce what I got working last time. Which I believe is this. Okay, so let's recap what I'm doing right now. So I just ran the OS, and the OS is currently configured to boot up, and it initializes the network interface card. And it initializes the NIC for reading. And then after the NIC is initialized, it boots into user space. And then user space has this small input dot, I think it's called, is it what, test input? Test input. There's this small app that runs in user space called test input. And so we're going to actually make more use of the functionality here later. But for the moment, we're just using this to test that the NIC is set up for receiving correctly. So often I haven't gotten the project after that. Happy with exams we'll do soon, I guess. Well, good luck with exams, dude. Hope you're gonna kill them. Is it like programming exams or what kind of exams? Also, what's up, Surge? Is that able to move? Yes, it's enabled to move, and I have it configured for a bunch of fun sound effects.
Damn, son, where'd you find this?
Yeah. Oh, it seems like the music is briefly stopped. All right, yeah. So yeah, I got my able to move here. Best streamer soundboard ever. Right, so user space is booting into this app, and I don't actually really understand how this works, but it sends an ARP request. And that's going to send a request out into the virtual network, and then QEMU is running some kind, like QEMU has some other, I guess, devices on the network, and one of them is going to respond to the ARP request. And it's going to send an ARP message to our computer that's running the OS. And since our NIC is set to, since the NIC is initialized to receive data, we should see some kind of logging being triggered when the packet comes in. And that is what we see here. And so the system comes up, we see a bunch of NIC initialization logging. Then it boots into user space, sends this ARP announcement, and then we can see these messages are coming from QEMU saying, and that's when we send the data out. And then lastly, we get this message, which confirms that a packet came in and it matched the packet filter that the NIC is initialized with. So that just shows that things are kind of working. So what I'm going to do now is I'm just going to clean up the state of my code a little bit, because it got kind of messy because I was doing all sorts of debugging and stuff like this. But the key point though was I needed to add this one particular QEMU option to enable some of these log messages, and the documentation in the coursework didn't say that. So yeah, that's critical. So here's what I'm going to do. I'm going to. Is there anything useful in here? Kind of. Yeah, this is sort of important. Okay, I'm just going to make a commit and initial commit. And we will clean stuff up later, I guess. I think we actually don't need the BAM bit. I'm just going to put everything here. I'm going to do a whip commit initial RX. Okay. Inexact mismatch. That's interesting. So there's other traffic coming in on the network here. You can take a look at what's actually happening. So I mean, I guess there's, interesting. So I don't know why. Oh, maybe it only finishes writing the PCAP when I quit the OS? No. So I guess, so here's the PCAP, and we basically just see two things. We see the broadcast message that comes from the OS, and then we see the reply, which comes from some other host on the network. That's all, but that's directed at us. Theories are done. Yes, it is software related. I have software testing lab tomorrow, then Android development after that. Okay, cool. All right, welcome again to everyone joining the stream. We got 12 people in the stream. That's pretty cool. So yeah, so basically had that as one commit, and then this is like this pretty critical commit. I'm just going to disable kimu.log file and enable E1000 tracing. Enable tracing to get more E1000 log messages about RX. We don't want them to go to a log file, just print them to the console. Okay, now we can kind of go back and clean up some of the messy code from last time. You know, actually what I'm going to do is I'm just going to reorder these commits. Oh, actually, no, I did that the wrong way. So, and then I'm just going to, my goal was to, okay. Okay, I kind of wanted to soft reset this commit so I could control it a bit better, but so I think there's a bunch of stuff I do need here, but there's some stuff I don't need. So bam. I don't need this UPE or MPE stuff. I'm going to delete that. What's up, Cypher Lo-Fi? Welcome. I do need to enable LPE. This is not used. B size offset, not used. So I don't need any of that. Get rid of those constants. So not implemented. Just say in manual, but not implemented by Kimu. So that, okay. And then what's going on here? This will all change also, I think. When we get, yeah, I have some new understanding about how to do this stuff, so we'll edit that in a moment. Okay, and then we're just going to write, okay, and we just write a couple bits. The enable, possibly not needed. Okay. Let's just run it again. Something is not working. Okay, what happened? What's going on? Did I? Temp. I'm just going to commit this and then revert it. Did I do something wrong here? So I didn't think I was doing anything very controversial. All right, what? So how do I hide this lazy git? Yeah, okay. Okay, well, I'm not sure what's going on. I literally was just running the OS and we saw it running and now it seems to be hanging. I didn't even do anything. I didn't do anything interesting. Let's quit. Let me. And what's even stranger, like I really. Pretty much just made a commit. I'm just gonna undo some stuff. And now it's working. And wait, that was okay. Now, so clearly something happened. So clearly something happened. Let's try that one more time. So these two things are commented out. I'm just gonna go extremely cautiously here. And that's working. Right. This OS dev stuff is kind of spooky sometimes. Things just break for no reason. So commits. Okay, so anyway, so we've confirmed that it's now time for a palm tree break. So I'm just gonna invite you to join me for a quick stand up and stretch. Right back. All right. What is up, Duck D's? Hello. Okay, so so it says, even though the driver can't receive the reply, you should see 1000 message indicating the packet was received and matched the filters error. If you see a mismatch, it means you messed up. Blah, blah, blah. Now you're ready to implement receiving packets. To receive a packet, your driver will have to keep track of which descriptor expects to hold the next received packet. Hint, depending on your design, there's probably a register keeping track of this. Similar to transmit, the documentation states that the head register cannot be reliably read from software. So in order to determine if a packet has been delivered, you have to read the DD status bit in the descriptor. The bit is set, you can copy the packet data out of the buffer, and then tell the card that the descriptor is free by updating the queue's tail index RDT. If DD isn't set, then no packet has been received. This is the receive side equivalent of when the transmit queue is full. There are several things you can do. You can simply return an error. While this approach works for full transmit queues, it's less justifiable for empty receive queues because The receive queue may remain empty for long stretches of time. Second approach is to suspend the calling environment until there are packets to process. Very similar to IPC receive, just like in the IPC case, we have only one kernel stack per CPU. So as soon as we leave the kernel, the state on the stack will be lost. We need to set a flag indicating that an environment has been suspended by queue receive underflow and record the system call arguments. Okay, so this sounds a little bit fancy. We will maybe do this, but for the moment I'm just thinking about doing kind of the simpler thing, which is their first approach, which is just to return an error, rather than doing this whole thing of like putting the calling environment to sleep. Record the system call arguments. Its complexity, E1000 must be instructed to generate receive interrupts, and the driver must handle them. Right, and so if like a user space environment asks us, asks to receive some data, and there's nothing there, it's saying basically we want to put that task to sleep by descheduling it. And then some point later when there actually is data, we will wake it up with the data. But that requires a bunch more kind of integration with the NIC. We need to make use of the interrupts and stuff like this, which we're not doing at the moment. So exercise 11, write a function to receive a packet from the E1000 and expose it to user space by adding a system call. Make sure you handle the receive queue being empty. And then this challenge is exactly what they were talking about here. All right, let's go. I'm pretty excited to try this. So what I actually learned in the meantime of doing some reading is that I'm just going to flip over to the relevant part of the manual. So the way that this is going to work is where is my helpful diagram? Copy this. Right, so we have our receive queue. And actually, here's how it's going to work. So the way this queue works is the OS on one side is the producer. That's actually the case with both of these queues. The OS is the producer in both instances. In the transmit side, it's producing these descriptors and it's pushing them onto the queue. And the descriptors basically point to some data for the hardware to send out. So the hardware consumes from the queue and pops a descriptor from the queue, looks at the data in the descriptor and pushes it out. So OS is the producer, hardware is the consumer. It's exactly the same thing for the receive side in that sense. The OS is the producer, the hardware is the consumer. The OS is producing these descriptors that are basically available buffers. And then when the hardware has some network data that it wants to give to the OS, it pops a descriptor off of the queue and copies the data into that descriptor, basically, or that area described by the descriptor. So basically, then that descriptor is consumed. And so what the OS needs to do is on initialization, it needs to fill this queue completely full with available empty descriptors that are ready for the hardware to pop. So its goal is to completely fill the queue. And a couple of details are relevant here. So I'll just copy this in. This specific point is important. So it says, oh man, that screenshot did not work great. Okay, so let's read carefully. When the head pointer is equal to the tail pointer, the ring is empty. And so when we fill the queue, we need to make sure to not do this, because in general, the way it works is like at the start, the queue is empty, and then we, like conceptually, we are pushing these entries on into the queue. And this like blue sort of thing means it's an available empty buffer that's ready for hardware. We need to be careful though to not push this one, which would make tail wrap around to the end, because that would be an empty queue. So tail, the farthest tail can go is over here. But actually, what we're still going to do is we're still going to populate this one and get it ready. It's technically not going to be pushed into the queue yet, because the only things that are in the queue, meaning they are available for hardware, are the ones that are before tail. And so tail always points to the one that's out of bounds. It's one past the end. And so this one is technically not ready for hardware, but we're just going to initialize it anyway. And then the way the receive algorithm is going to work is it's not that complicated. It's just when it's time to receive, we're going to kind of wake up and look at the state of the queue. And there's a couple of things that could have happened. Let's just say so what's the happy path? What's the normal case? In the normal case, the hardware has written like a bit of data. Let's say it wrote 2 buffers worth of data into the queue. And in that case, the queue is going to look like this. So forget these blue things. In that case, the queue is going to look like this. Oh, Twitch. I need to check my Twitch chat. What's up, Shushi Thrash? What are you doing? I'm writing a driver for a network interface card. Thanks for asking. I don't have a good system for allowing me to watch both chats of YouTube and Twitch at the same time. So if anyone has any ideas on how I can do that, that would be nice. I'm just watching the YouTube streamer monitor at the moment. That's how I typically do it. Okay, anyway, so what's the happy path? Let's say the hardware has written in 2 buffers of data. And then we wake up and we're like, okay, time to receive them. What we need to do is we orient at tail. We see where tail is. And we actually don't look. There's no reason to actually check the tail buffer to see if data was there. It's actually not ever possible for data to be here. And I'll explain that in a minute. But the most basic thing to do, we don't check tail. We start at tail +1, which is over here. Maybe I can have an arrow. So our cursor is kind of like over here. So we take tail +1. Tail +1 is the first candidate descriptor that might have some data that we care about. So we look and we see, okay, does it have a DD bit set? DD bit set means, that hardware has written to the descriptor and hardware is done processing this descriptor, and it's back under the control of software. And so that means software is allowed to touch it and read it and stuff like this. Hardware controls this range of descriptors starting from head inclusive to 1 before the tail, and then software, meaning the OS, controls from the tail to 1 before the head. And so if we see, is there a DD bit set? Then it's time to process the data. And so we go look up the data, and I don't actually know what we do with it. We pass it off to whoever was interested in it. For example, the user space process that wanted to receive it. And then after we do that, we process the data. It went off to user space or something. Then we mark the descriptor as free again. We processed it, we passed the data off to whoever, and now it's available for hardware again. And then we advance the cursor. We see, okay, what about this one? Oh no, sorry, actually, so I missed one thing. So we look, we see there is a DD bit. Yes. Step 2, we take the data, we pass it along to whoever is interested. Step 3, we kind of reset the descriptor, and then we point tail to be here. So this is now the new end of the ring buffer. And so that has effectively pushed this one into the buffer and made it available for hardware. And then now we keep going. Now we see, okay, DD bit, step 1, it's set. That means we can continue. So we take the data and we pass it along to whoever needs to care about it. Step 3, we reset the descriptor and reset the DD bit. That's kind of it, actually. And then last step, we point tail here. And then what's next? Now our cursor goes to the next one and we do the same set of checks. 1, is the DD bit set? No, it's not set. And so we stop. And then that produces this as the final state of the queue. Tail points at 1 minus head, because if we cannot advance tail to be here, because otherwise the queue would be empty, and then hardware would not, the queue would be perceived as empty by the hardware. So tail, the furthest tail can go is right here, and that is the end state that we leave the queue in. So that was the happy path. Let's talk about some other cases. And so we're back at our initial state. Let's say, so let's answer the question about, all right, no, let's talk about the case where no data came in at all, 0 data came in. We initialized the NIC to this state, and then now at some point later in the future, we're waking up and we're seeing, is there any data to receive? Let's run through the algorithm. So, so we begin at tail plus 1, right, over here. And what's the algorithm? Step 1, check, is the DD bit set? No, it's not set. Stop. We don't do anything. That means if the DD bit is set, that means hardware processed it and head advanced. But if the DD bit is not set, that means head is still pointing there, basically. So that's how that works for that case. And then now let's talk about the case where hardware had a ton of data to give to the OS, and it actually completely drained it, and the hardware emptied the queue, because this is a full queue. Let's talk about when the hardware empties, has emptied the queue. And just checking the stream, make sure it's still going. All right. Right. So the queue is full now. Let's say a ton of data came in. That means the NIC, basically, it had a piece of data, it wrote it in. It had another piece of data, it wrote it in. It had another piece of data, it wrote it in, et cetera, et cetera, et cetera, et cetera. So, interesting. Okay, what I want to do is sort of I'll just copy and paste these over. So here's what the state of the queue looks like. Okay, so it had some data, popped it in, and then what about here? What is the hardware allowed to do this? And I'm pretty sure yes. So last piece of data came in, hardware wrote it, and then now hardware pushed these to be equal. And then, so now the queue is officially empty because these two are equal. And that's the rule. Hardware has done everything it can within the constraints of the queue space. It pushed in as much data. And from this point on, if more data comes in, that data is going to be dropped because the hardware is not allowed to go further. The reason it's not allowed to go further is because, so for one thing, the queue is empty, but also the secondary reason is because tail marks the first descriptor that is owned by software. Owned by software means hardware is not allowed to write to it. And so in this situation, hardware still owns this descriptor. Hardware owns the descriptors between head and tail -1, which is just a single thing. What's up, Ivan? Greetings from Brazil. Nice. And so hardware owns this final one. So it pushes it in, advances this, and now it has nothing else to do. One thing to notice is that this is asymmetrical to the producer side. So hardware is the consumer, software is the producer. The producer, as I was saying earlier, software is not allowed to push the tail so far that it would empty the queue, because that would defeat the whole point of it trying to put things into the queue. So the farthest that software can push tail is here. However, the consumer is allowed to empty the queue, and that produces this condition. And what this means is that hardware will never populate this descriptor. Hardware, even in the worst case scenario of tons and tons of data coming in from the network, hardware head cannot go past tail. So it will stop here. This means that tail will never have a DD bit set. Hardware will always stop here. And so that is the explanation for why in our receive algorithm, we do not need to check if tail has data. Tail, we can assert that it doesn't, but tail will never have data. If tail had data, that would mean the hardware violated the contract and pushed data into a descriptor that is not owned by hardware, that's owned by software, and that would be a violation. We can assume that's not the case. And so that means we never need to check tail. Tail will always be an empty buffer, and the first eligible buffer to check will be tail +1. So that was kind of a long explanation, and now it's time for another palm tree break. But after that, we'll get into coding. So I'll be right back. Feel free to stand up and stretch and get some water. All right, so with all that said, let's start coding. So I'm just going to code basically what I just described. So what we need to do is we need to write a function to receive a packet from the E1000. So I don't have any idea what the interface is going to look like really, but I'm just going to start sketching something out. Okay. I never actually did configure Clang format. So we're going to have receive. we don't actually need the end of packet, I think, for the moment. Return 0. And what does the API look here? So in the case of transmit, we received a buffer of a certain length and pushed it out. In the transmit case, we received a buffer. In the receive case, someone will need to pass us a buffer to write into, I guess. And just for simplicity's sake, I'm going to require that the buffer be large enough to handle the maximum packet. And so when kind of designing the queue size, I made a very simple design. It's the most simple way you could go about this. I just basically have this huge static allocation of array of memory for the receive buffers. And just so what happens is I was talking about this ring buffer of descriptors. In my very, very simple implementation, each descriptor points to what I'm calling a backing buffer, which contains the actual storage space. And each of these backing buffers is the same size, and they are all laid out right next to each other in memory. And in particular, they are 2K bytes. RX descriptor backing buffer size, because that is greater than the maximum Ethernet frame. And so I'm guaranteed that one descriptor can always hold one Ethernet frame, basically, which is the simplest way to do this. And so what I'm just going to do is if len is less than krx buffer size, return -1. I don't have a great error handling strategy at the moment. I'm just going to do the simplest thing and return a bunch of negative numbers. Yeah. Okay. And that's pretty much the only reason length is going to be used here, just for this check. And now we have, so now it's time to actually implement that algorithm I described. And so what we're going to do is, it's going to be kind of similar to this, maybe. We're going to read the tail, and it's RDT, I believe. RX descriptor tail. Digitalize, what is up, my dude? Welcome. So yeah, we read the tail, and then we get the next index. And just keep in mind, like, all of these namings are super preliminary. In production code, I think, yeah, I would take a lot more time to think about what these are named. But we get the tail, and we get tail next, which is just wrap index. Wait, what? I want tail +1, right? Actually, what's going on here? That was actually kind of weird. I think this might be kind of buggy, actually. Wait, what? Why is tail not incremented here? Bug. So in the transmit algorithm, the idea is to look at the tail, and yeah, this is totally buggy. I'm pretty confident there needs to be a +1 here. But we'll get back to that in a moment. But it does not make any sense why I would just wrap the index of tail, which would not do anything. back to here. So we get the tail. We also get tail next index. Yo, what's up Insta Headshot? And also what's up Gangsta Lobster? What's your favorite text editor? My favorite text editor it's probably VS Code with Vim mode, I would say. That's what I'm using now. Okay, so we get the tail, get tail next. Then we can do a few things. We can assert that tail descriptor status, right? So I wanted to assert that the tail descriptor never has the DD bit set. And I just need to go back and find... Okay, we need to go into the manual. We just need to find out... I believe it's pretty simple. It's just the 0 bit. And so what we're looking at is the descriptor is like this structure right here. So this is the descriptor structure. This is and this is the status. And we are trying to check this specific bit. It's the first bit. So assert that DD. I think I did this here. So there's already a constant actually for the DD bit, stat DD. Just curious. And likewise, there is already a constant declared for the DD of the received descriptor. So what I'm just going to do is rxd stat dd not. Always be available, not written by hardware. How are you managing ideas in Miro? I am managing my ideas in a very sloppy way. I basically just make a new area for every week, and I just kind of copy and paste diagrams and documentation that's relevant. And I like have this big ass board going back a year now, and it takes this kind of funny shape, but it's kind of disorganized. It's just kind of like a scratch space. So we're asserting that tail descriptor, and then now, I'm going to maybe make a cursor actually. Current equals tail next, right? And what's the algorithm again? It's like, yeah, it's like while, so while we're pointing to a descriptor that has the DD bit set, do stuff, and then, yeah. It's chaotic and cool at the same time. That's the goal, chaotic and cool. While current status and rxd stat dd process the descriptor, and then current is going to be equal to GTX descriptors, wrap index. Oh shit. Okay, I don't know how I don't how do we do this? So we need to bump to the next descriptor. I mean, we can also keep, you know, we can keep track of you know, let's just use a int maybe, tail next as the cursor. Yeah, I mean, there's a bunch of different ways to do this. I think, you know, the easiest way I'm just going to sketch out is like actually with an infinite while loop. So, int cur tail next. So current cur desk equals oh shit, equals, right, cur. So we have the index if cur desk does not have rxd stat dd, then we break status. Right. So here we're just checking, okay, cursor points here, we do the check. Does it have the dd bit set? If it doesn't, bail out. Otherwise, we process the descriptor. And yeah, probably there's a better way to formulate that loop, but for the moment, this is the easiest thing to do, I think. Because at the very end of the loop, we can just do cur, maybe I'll do cur index equals wrap index cur index plus 1. Right. So basically, rather than tracking a pointer, we're just tracking the index and then looking up the pointer. So now it's time to process the descriptor. And what does that mean? We need to copy data back to the caller. So I guess I think I guess what the semantics of this is going to be is we're just going to like receive one packet per call. Like every time you call this, you get one packet maybe. That would be pretty simple and a nice way to go about it. The alternative would be to kind of like loop through and pass off as much data as we can get, even if it's multiple Ethernet frames. But I kind of don't love that. I think it's a little bit cleaner for the moment just to have you have this interface be like you call it and you get one Ethernet frame out. And you just process the frame and then call this again when you want another frame, which means we actually don't need the loop here. Because we're guaranteed that every descriptor, like, can contain an entire Ethernet frame. And so we actually don't really need the loop. We're planning on doing the challenge part for this course after this lab. I'm giving that a maybe. I'm not quite sure. Yeah, I didn't do any of the challenges, right? So I could go back and do all of them, or the ones I'm interested in. But I'm kind of itching to start my own OS, and mostly I'm just kind of tired of working within this like JOS environment, which is still like very kind of alien to me. So I think I might not. Yeah, I might just start off on my own. With my own OS, I think I probably would take some similarities from JOS, since it's just kind of what I'm familiar with and what I know. And so I might be able to do some of those challenges just in the context of my own OS. Yeah. Word. Okay, so let's get rid of the loop. All right, we're not doing a loop. All right, let's rewind. Let's say we're not doing any loop. Let's say all we're doing here is when the function is called, we look at here and we see, is there something? If there isn't anything, we just return. And maybe we return in some kind of error code to say there's nothing there. Otherwise, all we do is just process this one, and then that's it. And then this goes here, tail goes here, but then that's it. We don't even bother, like maybe there's even something still here, but we don't even bother to process it. We require that the caller calls receive again if they want to get more data. And they basically just kind of need to busy loop. Yeah, that would make most sense. I'm definitely itching to do an ARM-based kernel after I finish the 2021. Yeah, man, that sounds cool. I'm also itching to kind of try some different like architectures, but I'm also itching to do to really get into the details of x86 and check out some of the weird stuff that they have there. So yeah. All right, that's gonna make this a lot easier. So we basically say assert, and then we check if tail desk status and rxd stat dd return -2. So not tail desk, tail next desk. Did the next one have any data? If not, bail out. Otherwise, time to process. I'm using a lot of embedded stuff and also the GBA, which I want to emulate. Nice, cool. I didn't, wait, Game Boy Advance, really? I did not know that. That's cool. So time to process the descriptor, which means memcopy into buffer from the backing buffer, right? And so that's going to be tail next desk p buffer physical addr and tail next descriptor buffer length, something like this. But we need to convert this into a virtual address, I believe, because these descriptors actually store a physical memory pointer, So we need to convert that back into a virtual address. Yeah. So copy the data back. Now we just need to reset the descriptor and then advance tail. Reset the descriptor means what? Status equals 0, something like that, I think. We can just check out what this looks like. So we almost kind of don't even need to clear the status, I think, because this whole region is written by hardware. But maybe it's just good form to we could also clear out the length while we're at it. I don't know. Actually, no, we shouldn't. No, yeah. So the length is provided by the hardware of how much data it wrote into this buffer. Possibly not needed. But you know, we could buffer length. We could try doing this. Lastly, advanced tail. I'm just going to. How do we do this over here, right? So we wrote at tail next plus. So advanced tail, what does that mean? So tail next is actually pointing at what we're looking at. So we have, right, tail was here, tail next is here. We saw the DD bits. Oh man, 20 seconds. All right, be right back. Yeah, well, Ivan, I will get to that question in 1 second. So tail next points here, and we want to point even one further, which is actually no. Wait a sec. No, we want to point tail directly at tail next. So all we're doing tail next. We just point it at where we are. And that's it. And when we return 0. Try to receive one buffer from the ring. Returns 0 on, 0 on success. On buffer length. Too small to no data available. Look at that. All right. I'm a SAP ABAP developer with some experience in C. I want to learn Linux kernel development. Where should I start? Are there any recommended books, tutorials, or hands-on projects for beginners? And Angela says, follow MIT XV6 course. Yeah, I would say, I mean, if your goal is to specifically learn about Linux kernel development, there are a lot of resources specifically for that. There's books about Linux kernel development specifically. And so that's one option. You could just read all these books like Linux. I think there's literally a book called Linux Kernel Development. You know, there's resources. That would be okay. That would be I mean, apparently there's YouTubers that talk about this. So that's kind of route number one. Route number two, I guess, is you could learn about OS development in a very generic way, and then try to use that knowledge in Linux kernel development, and that might help you. That'll be like a much longer road. I sort of feel like if you feel very strongly that you specifically want to learn Linux kernel development, I think the most direct path would be to actually just focus on that. There are a lot of resources on writing kernel modules specifically, and I think that's probably a good start. Apparently, there's also a course. I don't know. Write some kernel modules. I mean, the first steps would just be like learning how to build a kernel and stuff. The XV6 thing is more of the second route where you like go really from a foundational perspective. You like learn how operating systems work in general. But even if you have that knowledge, it will still take you some time to adapt to Linux, which is it's like a whole beast of like an environment. But you will probably be able to get going quicker with those fundamentals. So I guess it depends on how much background information you have about operating systems. For me, that's kind of why I'm doing this. I think it would also be really cool to do Linux kernel development someday, but I sort of don't feel like I have the background info. What's up, Ismail? Good to see you. Happy Sunday hacking. How hard is it to contribute to Linux kernel? Probably you could ask 5 people. They would all have different answers. I can tell you about my experience because I actually have contributed to the Linux kernel, but it was really small. Like 5 years ago, I found this bug. I found like a very stupid bug in the kernel where like they just said the wrong thing in this print statement. This is the print statement that runs when the killer kills a process, among other things. And basically there's some code that it prints the registers and the stack of, I think, that the task that it killed, but and then it also like disassembled some of the bytes, or like printed some of the opcode bytes that the instruction pointer points to. And if it couldn't get those, it printed bad RIP value, which sort of kind of suggests that the instruction pointer got corrupted or something like that. But that's like not true. The reason this could fail is like for this whole thing I described, because like maybe it could be paged out. So this was like not easy, and I had to also ask a friend for help. I discovered it because I was doing doing some research at the time. I had this blog post where I was triggering lots of kills because I was doing some research about demand paging, and I wrote this blog post called "What They Don't Tell You About Demand Paging in School." And I was triggering lots and lots of kills, and I was reading the logs, and I just noticed this thing constantly. I was like, "What is going on? That sounds like someone is exploiting my machine right now." That's not what happened, obviously. It's just like this was wrong. So it took a long time, and I also wrote another blog post about my experience with submitting a patch which was really cumbersome. You have to like email stuff and all this stuff. So basically I would say it wasn't easy, but I was able to do it with a bit of help and guidance. So it's not impossible either. Cosmo, thank you. Digging TF out of your channel, bro. Appreciate that, man. All right. Let's, so I think I did it. Let's compile. Does the kernel build? The kernel builds. Let's fork. Let's maybe do a commit. So this is almost certainly a bug, actually. I am just going to run this. Are we still working? So we're still working. So what just happened? We are still seeing that it's sending the ARP request. We're seeing the messages saying that QEMU is legit sending data out onto the network, which means the transmission is working. And then lastly, we still see this logging message, which verifies that the packet was received by the NIC and that it passed through the filter. So we haven't confirmed that my receive function works yet, but we basically just kind of confirmed that this thing worked. So I'm going to just amend that into here, implement basic transmit. Okay. What's next? So basically, I think this is like ready. This is like a commit. Basic 1000 receive. Okay. And what's next? So yeah, how's that music, by the way? All right, I finally got my streamer set up to be a bit more professional, and I have like a bit of monitoring so I can actually listen to the way the stream sounds. I never had that before. All right. So write a function to receive a packet and expose it to user space by adding a system call. Make sure you handle the receive queue being empty. So I did that. So now it's time to add the system call. And this is a little bit of grungy work, but I think it a bit low. Is the audio a bit low, actually? Or the music is a bit low, you're saying? I can bump it up a little bit. I think last time, I felt like last time the music was a bit too loud, actually. So, yeah, appreciate the feedback though. Yeah, yeah, I still like, all right. Check 1 2. All right. So now it's time to add the system call, which is a lot of boilerplate because I never really invested into making it easy. So I'm going to add this call. It's called network receive. How do you spell receive? No. Receive, okay. Sys network receive. And it's going to be very similar. Receive, and pretty much just like transmit, user space is going to pass in 2 arguments. receive, and except it's not going to be const, and we still need to verify the permissions. We need to validate that buffer to make sure it's a user space buffer, and then we call receive. And I guess I need to add this add declaration. Did that work? That did not work, I think. I need to add a prototype here. Len cannot exceed 128 currently. I don't think that's true anymore. Len cannot exceed. Len is limited by this thing, which is now 2048, because we're just, yeah, so this is actually wrong. And I'll just take a moment to I'll just quickly amend this into, you know what? Yeah, LazyGit has this awesome feature where if you hover over some changes in your working tree or staging tree and hit Control F, it will point to the commit that sort of like introduced the diff you modified. So for example, this is the diff I modified, and I want to actually amend that commit. And so I can just do that super easily. So now that commit doesn't say that anymore. Yeah, it's also kind of interesting. I was expecting it to add a, maybe that got added in a different file. That got added here, actually. Is that correct? Implement basic transmit. Actually, yeah, it is. Okay, so because that's just the prototype for the function we're adding. So, okay, so we have our thing. We don't need to do this. And what else is involved in adding a system call? Let's just check. This is the commit that added the system call for transmit. And it did a lot of the work for us. We have a couple kernel changes. Next, we need to change some stuff in user space. So we need to go to lib/syscall network transmit. Okay. Receive. This is not const. Receive. What is that one again? Check. It's just this Boolean. Okay. And then we just pass in the buffer and the length. So that's pretty easy. And then lib. So now we need to add it to the libc. So now what we're looking at is this is sort of like the libc part, because user space is going to need to call some kind of like user space function in libc to trigger that syscall, and that's what we're doing here. I really need to learn madgit one day, the Emacs package. Right now I do all my git by typing in the command line, but a lot of people seem to enjoy tools like LazyGit and such. Yeah, I think it's also super valuable to learn how the command line works, but I do think that there are better tools than the command line. And a lot of people just don't know about them or just live with command line Git for a long time, but I think there are definitely better tools for a lot of use cases than command line Git. libsyscall, or no, wait, was it? libsyscall, inc syscall.h. But I already did that. So I have a relatively complete patch now that adds the syscall. And I have syscall.c. Const, it's not const. Nice. So I think I basically have it. Just stage these and take a look. So this thing, this thing, this thing. I did not want this actually. This thing and this thing. Okay. What was my message? Okay. Add basic sys network receive. All right. Nice. We got 26 people in the chat. Hello to everyone in the chat. All right. So I wrote a lot of code, but we haven't really executed it yet. And I think now it's time to do that. So at this point, I'm pretty sure, well, hopefully the code is working, but we have attempted to initialize the receive side of the NIC. We confirmed that that was kind of working. Then I just kind of cowboy coded a receive function to actually get data out of the ring buffer, and a system call to allow triggering that, but we didn't run that. And then now we're going to try to do that. Did I change my Vim theme? Maybe. Honestly, I don't like. I think maybe I changed some iTerm stuff. I barely pay attention to the color scheme stuff, to be honest. Not that I can really remember. Okay. So the next step, exercise 12, implement net/input.c. In the network server input environment, you will need to use your new receive system call to receive packets and pass them to the core network server using this IPC message. These IPC input message should have a page attached with a union and its IPC with its struct, something filled in with the packet received from the network. Okay, let's try to do this. Net input.c. So here's my output just for reference. And also just for reference, let's pull up that handy diagram. So here's the block diagram of how this stuff works. Yo, Bacon, what is up? What's up, Bacon? Nice to see you. Yeah, it was fun hanging out in Kaya's stream the other day and on Discord. Thanks for joining here. Bit of a different flavor of stuff. Yeah. All right. So specifically, so we were working here. We were working in the kernel driver for the RX ring. and that is kind of working. Then I implemented just this basic system call that exposes that receive function. And now we are rising up in the world, and we're right here. We are working on the input helper environment, which is a process that has just kind of one responsibility in life. It sits in a loop forever, I think, and is just calling receive, calling the system call to receive data. And if there was any data received, we pass it on to the main network stack. Yeah, nice diagram. Yeah, I didn't make it. It's the diagram that they provided for this like coursework right here. But yeah, true. It's a great diagram. All right. And we hit the palm tree break, so I'm just gonna stand up and stretch for 20 minutes. Feel free to join me. Be right back. All right, so, yep. So Flames, are you using any sort of special libraries? Yes, good question. In general, no, except for this networking stuff. There's the major exception to the no libraries thing is that for the network stack, we're using this project called Lightweight IP. Also, like, not my decision. That's just like how the course works. And honestly, I don't really know what it is. So obviously I can read that it's a TCP IP stack. To be honest, I have fairly weak understanding of what that like actually means. Like, okay, of course, sure, I can see that it implements protocols, but I have kind of weak understanding of like how you use it, to be honest. I didn't like integrate it. But apparently, yeah, it's like a network stack, and we are running it in user space. And then we just have this like integration glue that actually connects it to the kernel, and that's like the stuff that I'm working on. Okay, input helper. So you'll need to use your new system call to receive packets and pass them to the core network server with some IPC message. We're going to get a nice while loop going on here. Read a packet from the device driver. It's basically going to be the opposite of what we see here. So what jar receive buffer. You know, I'm just going to declare a stack variable for the moment. Size of, whoa, receive buffer. Yeah. Okay. Right, there were a couple. So if ret equals -2, that means there was no data, so we continue. I don't know. Sorry, ret is 0. And so that was the easy part. The hard part is how do you send IPC messages again? I do not remember how to do this. So who's a good example of IPC send? So, okay, also, so here's just the prototype. It takes an environment, a 32-bit value, and a page. And some permissions. Right, and then is there lib.h. I'm looking for these there's all these IPC ns.h. These are the IPC requests. Here, okay, here's what I'm looking for. So there's this like weird union thing. It has been a hot minute since I have sent an IPC message. Who are the other people sending IPC messages? Serve.fs, file. But yeah, so okay, what I need to do is call IPC send. So I need to allocate a page for shared memory. Initialize the union. And then pass the page here. So I need to allocate a page. And do I need to, so what does this union look like again? Ooh. So there's this, okay, yeah. So there's this union that occupies one page. And it can contain a bunch of different things in it. And we are interested... All right. So ns... the input IPC message. Let's take a look at output one time. So with the output, we call it and there's like this just random area of memory that they chose. Some address minus queue size. So what's up with that queue size? Okay, very mysterious, but anyway, this is a kind of arbitrary address, and when we pass that in here and the IPC receive goes through. Okay. It's going to be mapped to equivalent data that was prepared in the sender's side. Yeah, and it's going to, but interestingly, it is just a GIF packet, actually. It's this thing. Wow, okay, so it's just saying, so we're actually not, we're not using any of these special structures. These are used for other IPC messages between other parts. I don't know, other parts of the system, like there's accept and close and bind and all this stuff. And those are messages that go from the actual application environments to this thing, I think. Oh, it's documented here. So yeah, I was getting kind of confused between receive and send. Those are IPC messages that are for the actual user applications. And so that doesn't concern us. We are implementing this like special helper process, and all it's concerned about is passing a page with a struct GIF packet output, unlike other messages, is sent from the network server to the output environment. That's this thing. That's not what we're focused on. Okay. So that kind of clarifies things. So I need to, first off, I need to allocate a page somewhere. And I think it doesn't really matter. And I sort of dislike how they are just like hard coding addresses. And if I can avoid doing that, I'm going to avoid doing that. So what I'm going to do is take kind of a influence from the network driver and how I, oh shit. Union. Yeah, and so I'm just going to allocate a page size. Does that work? No, it needs to actually be a page, right? Page. That's interesting. So I'm just going to allocate a page of memory that is page aligned in global data, because that's my favorite place to allocate things. And dang. Okay, so no, I'm stupid. Wait, am I? So this buffer is going to contain a GIF packet. And what is a GIF packet? It is, okay. Okay. I'm just going to alias the pointer. Yeah, packet equals G receive buffer. So I need Do I need? Yeah, I need the cast, I think. And then the warning goes away, hopefully. Yeah. So this attribute magic, this enforces that this buffer that I declared is aligned on a page size boundary or a 4K boundary, which is important here. If I didn't have this, then there would be no alignment requirements, and I think it's pretty unlikely that that variable would be aligned on a 4K boundary. We can actually do an experiment. So if I build the kernel, and then if I go to kern, and then if I do readelf, which is the best command, and I look for G receive. Hello? Oh wait, yeah, no, it's not in the kernel. This is in user input? No, what? Net. If I do a readelf and do test input, and we look for G receive, we'll see the symbol here, and we can see the alignment information, this 4K, and you can see that it's aligned because these bottom 3 nibbles are 0. So as like a fun experiment, let's remove that. And then let's recompile the kernel. And then let's rerun this. Oh wait, no, okay, so I was a little bit wrong. This column is not the alignment, it's the size of the variable. And so the variable is 48096, and we can see that it's not aligned on a page boundary. So that's the reason, that's the concrete reason why we need this alignment attribute, is to make sure that it's aligned. So patch byte, quite funny, we do all these optimizations in C and low level, yet none of these apply to web dev. I mean, yeah, they're just different worlds, they're different domains. The coolest stuff I have seen. Nice. I'm happy that you saw some cool stuff today. So basically what I'm doing is I'm going to allocate the raw page here. Oh man, Ultron, I'm sorry my bot censored you. I briefly saw the message. Dude, the heavy metal font motivates me hard as F. Yeah, I'm glad you appreciate my heavy metal logo. Yeah. I'm a fan. So I allocate the memory here, but it's just the backing memory for this structure that I need to populate. And then I can pass the pointer off into this IPC message. And so I just need to have this local variable that aliases and points to that buffer so I can actually like reference it and write to these members. So, and actually now that I'm doing this, I realized I made a mistake with my syscall. I never made it pass back the amount of data that it actually wrote, and I think that's important. How did I fix my C include a header VS Code IntelliSense issues? So I think that was a while ago, and I think I fixed it by not using ClangD. If I remember correctly, I mean, I've been using just normal VS Code, C, C++ in IntelliSense, or the C and C++ extension. And then I briefly tried using ClangD, and it screwed everything up, which was very sad because otherwise ClangD is really good. And to this day, I am not using ClangD. So yeah, readelf is such a good program, by the way. If y'all are not using readelf, yeah, check out readelf. This you can look at so much cool stuff here. The N is a N. N is N not equal A, and I have no clue what that message means, Mark. Compile DB, I think is what you know. Interesting, okay. Anyway, I think I need to basically, I need to know how much data I'm just gonna code a little bit JP data. So this is what it's gonna look like. And I like bitmap stack. And we're just gonna do size of int. Yeah. No. So basically what's happening here is we have a page and we have one int followed by the entire rest of the page for a buffer. And so I'm passing in the pointer. I need to get the address of this. I'm passing in a pointer to this region. Maybe a visual is helpful. It's not that complicated. We just allocate a page of memory, and then basically this is the JP len, and then this is the JP data, and then packet points right here. And I'm just passing in a pointer to right here into the receive system call, so it writes into this area. Love ClangD had same issues. If you ever had any issues with Make, you can use Bear. Yeah, I think I was using Bear. Get Steve on my page. Yo, I think I was using Bear. But something didn't work and I didn't feel like figuring it out, and I've just been not figuring it out ever since. Is it already time for another break? All right, be right back. 20 seconds. All right, but I think I know what to do now. So I'm just going to assume sudo need to make the syscall ret num bytes written. I think that's important. So otherwise, we do some, I don't know, checking on the return code. Try going to the link you shared, but I don't see any content. I don't know for the course. What what link? Bacon, I don't like what, sorry, I don't even know what link you're talking about. Okay. So what we need to do is then we do packet jp len equals ret, basically. And then we can do the IPC send. And I need to pass in the the MIT course. Let me just use the chat bot to get the link. Does that link work for you? I think Kai's Discord on. All right. All right. So IPC send NS ID in 32 value, which is the IPC. Doesn't work, really? All right. Weird. I don't know. That link works for me. I'll check out your screenshot later. But it's pretty odd. So we need to send IP, and I need to send an IPC input. And we pass the packet and some permissions. What are the permissions? The permissions, I think it just needs to be a read-only page. We're just sending, like, we're not sending data that it's going to write to. Yeah. All right. So I think this is basically what I need. Okay. CC send perm, and then again, who's a caller I can look at for an example. I think this is basically it. PCE, PTP. Word. All right. So we need to pass in the length, and so let's go ahead and do that now. So we need to go to our syscall, and right now we're just returning 0, but int buffer length equals. Or we could just not do this, or we don't really need to reset it, I think. So I'm just going to return this thing, right? Which is this uint16 t, which is a little bit inconvenient. But I'm just. Do we get the warning? Maybe. Also interesting. Passing argument 1 incompatible pointer type. That's unrelated. That just So what does this thing take? This thing takes just a char buff. So I need to cast this to char. All right. Yeah. So that is going, and I think so. Now it's interesting that it doesn't warn me that there's like a conversion here between uint16t and int. But maybe that's just because like int can just fully receive a uint16t losslessly. So the syscall is now going to return this length field, which is the amount of data that the hardware wrote into the buffer. And then we can use that here. So we do our system call, we receive into our shared memory area. We check the return value to make sure that like the length should always be fine. And then if there was no data, we're just going to continue. And lastly, if there was actually data, and maybe or red equals 0, in case weirdly if like no data was written somehow, I don't know, if no data was written, we don't need to do an IPC message. Otherwise, cert ret greater than 0. I don't know, there's a lot of asserts. But then we set the length field, and this is actually where we might expect a warning, because now we're actually assigning, no, it's an int. Okay, never mind. So now we're just assigning the length and then passing the message on. And that compiles. So what now? Now I think it's just time to test it. Now I think it's time for a moment of truth. Yeah, all right. So we need to just run the test input thing, which is what we've been doing the entire time. And what should we see? We should see waiting for our packets, waiting for packets, blah, 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 multicast, input, and then a bunch of hex dump stuff. All right. Moment of truth. Let's do it. That did not work. And that's the same issue I was having at the start of stream. What is going on? Something is really going horribly wrong. Yeah, something is really, I don't know what. I was so hopeful. Things were like working for a long time. So that's a bit of a bummer, but yeah, so I'm gonna go in here. Right, we just want to fix this up. And then we just have our basic impl basic inputs. Let's see. So what? This is crazy. It like randomly stopped working at some point. So what about here? It's also not working. Oh. Was there anything I need? Actually, no, I do need this panic. Wait a sec. True. Do I need the test? No. Do I need this thing? I don't think. Maybe I do. Maybe that's it. Ooh, kernel panic. Sheesh. So, wow, what happened here? So if I comment this out, apparently that did not matter, but also this TX thing changed. What is going on? So now my assertion is failing. Okay, I'm going to revert that fix. Is there something? Okay, that's bad. Received page file from kernel mode. So, all right. All right, let me go back here. Let's just maybe it's due to this. Okay. At least we're back in a somewhat sane state. So it seems the problem was something to do with this. Actually, no, this is commented out now. This is very weird. Okay, but if I undo this return, and run test input, I feel like something is not right here. I feel like something is here. Okay, if I comment this back in, maybe. So now we're not crashing anymore, right? All right, thanks, Bacon. Okay, that was weird, but we're not crashing anymore. But now if I remove the return, we are asserting. And the interesting thing is we are asserting on the transmit side. But what if I remove, so if I remove this change, I think that's like, we're still seeing this assertion fail. Wow. Okay, interesting. What is going on here? And now it is properly crashing. But I feel like it's changing. I feel like it's actually changing behavior. It's like a little bit non-deterministic. Wow. That is interesting. So in this case, it actually did send data, but then it crashed later. Okay. Wild stuff. But that doesn't happen every time. Sometimes it's just asserting. So here's a reason why it's good to have asserts. Maybe. So then sometimes, oh wow. Crashed. And sometimes it asserts. Okay, so we have some kind of, just like kind of gnarly. And the strange and interesting part is that these crashes and assertions, they happen if I run the code in the input process. If I disable this, then what happens? Everything is stable. Okay, right. No crashes. No, okay. So weird. How would you begin to debug this? So actually, I'm not totally surprised by this, because I never actually really tested that transmit code. Like, I have this function for doing the transmit, and it has only ever really been tested in a very light use case of sending one ARP packet, and that's it, because the system never did any more transmissions up to right now. Like, up to right now, the only transmission that ever happened was a single ARP packet transmit. But what we're slowly introducing now is when I enable this input helper, we've kind of like completed the system a little bit. And so now I believe what's happening is, I don't exactly know, but I think we sent the ARP request, we received, but it like crashed pretty immediately, so that's kind of strange. My working theory would be something along the lines of, number one, we send out the ARP request. Number two, we receive the ARP response. Number three, it passes through the RX ring into the input helper environment, which number four, triggers something over here, which, I don't know, sends more data or something like this. So, yeah. But at least it's like kind of under control. So things are kind of working now. It's just the problem is, as soon as I enable this function to start doing stuff, what happens? Oh man, sending ARP announcement and then kernel panic. What's up, Fahim? Hey man, I have a question. I just found your video. Can you tell me what is the best place to start it? If you're asking about where to start watching my videos, I can't help you that much. It's just like a lot of videos. What I can say is the interesting stuff only happens from like week 13 or so. Like, don't watch any of the videos. I don't know. I would not recommend really watching videos before week 13. Week 13 is when I start actually doing... It's when I restarted the whole project and started using this JOS thing, which I've been doing ever since. So that's my recommendation. All right, well, I think I'll go a little bit longer today. This is interesting. And yeah, it's a good question. How do you even start debugging this? What I want to know as a very initial start is like how many transmits are being triggered. I'm literally just going to do this. And I'm just going to see how many times this thing gets called. All right, so in this case, it gets called once. We happened to hit like the weirdly non-deterministic case where it actually crashes. Let's try it again. Here we hit the other case where it hits the assertion. My question is, why did it trigger a page fault earlier? Maybe trap intentionally and see register values or something. So with the, I'm just gonna take a screenshot of both of these. I already kind of did, but yeah, let's go back to these screenshots. They're very, very interesting. With our new, we didn't actually learn something too new just now. We just, in both cases, it's just a single transmit. And so, yeah, why did it trigger a page fault earlier? I'm going to write some guesses. Guess number one, there's undefined behavior that causes non-determinism. Like basically what we're seeing is some of the time it is successfully doing the transmit completely, but at some point it crashes a little bit later. But sometimes it does not even do the transmit. It like asserts extremely early into the transmit. Oh, interesting. But maybe it's due to how the ring buffer is initialized. Is there some way there is some non-determinism? Wait a sec. Okay, wait a sec. I have an idea, actually. I'm not totally sure, but here's where I enable the transmit side. And it happens like kind of early. And then there's a bunch of other receive side initialization that happens. I'm wondering if potentially moving those to be like next to each other changes anything. So my guess is probably not. Nope. So I don't think that changed anything. Because we're still seeing both. We're still seeing both, but it's much more rare for the page fault to happen now. It actually only happened once in like all these tests, twice now. I tried moving the TX and RX enable right next to each other. Seemed to make the page fault be way less often, but it happened 2 times out of 12 something. But what in the world? I don't know. Spooky. What's up, Aegeans? And the interesting part is it's on the transmit side. I'm actually curious, does this, like, what is running here? Maybe I can name this a bit better. Input. I'm curious what yeah, so like obviously this code is running. What is running though? This might be something very stupid. So we trigger the syscall. So wait for it to GDB into the trap handler and check for the bytes received. Maybe. I mean, it's definitely possible to GDB the trap handler. It would be very interesting to know where that page fault is, and get a stack trace there, for sure, yes. So I'm going to keep that in mind. I'll add it to the list of ideas. There. So what I'm ptrace, I think ptrace is a bit different. Like, mostly the 2 ways I debug this are like 1 with the prints and the panics, and then 2, I actually do use GDB quite a bit. And so this is interesting, actually. Oh, wait a sec. I have an idea for the non-determinism. I wonder. So there's this thing called serve.c. I have an idea for the non-determinism. It's because there's this, back to this diagram. This whole thing it's like a parent process. And then it forks 2 children. And they both do stuff. And I think the order of their execution is non-deterministic. Maybe. So the theory is something like maybe sometimes, like maybe most of the time, the input helper gets execution first. But some other times the output helper gets execution first. All right, quick stand up break. Be right back. But yeah, something like that. Yeah. So, idea. Yeah, some kind of race condition. Let's input. I'm just gonna spam some print input before syscall. Put receive after receive before IPC after IPC. Okay, so that's I'm spamming a bunch of prints here. I will do the same for output.c. And I expect we will see output before IPC receive after for transmit, and I still don't really know what's going on, but I know that oh dang, I forgot to add new lines to every single one of these. That sucks. All right. All right, we got new lines in the house. And debugging is just faster. Maybe. I think both might potentially play a part here. What are we seeing? What? So, again, screenshot for some tourism and debugging purposes. All right, let's run it again. Now that is interesting. Teaches how to bypass DEP and ASLR points. That will have to be for another time, my friend. So check this out. Check this out. So this is interesting, right? We're getting a bit more information about the nature of these two problems. For the assertion, it's like it spams all sorts of stuff. Output, then input. But over here, if it transmit print, it doesn't page fault. If transmit prints, so transmit, It's something. There's a very interesting ASLR discussion going on. Man, I mean, yeah, quick side note about ASLR. I mean, yeah, like in general, to bypass ASLR, you need an info leak. Like exactly what kind of Eve said. Well, it depends on what kind of ASLR you're trying to bypass, but you need to be able to leak memory. Yeah. All right, back to this though. So it seems like we're seeing kind of holy crap. Wait a sec. Okay, check this out. Check this out. This thing was super long, right? That, like, such a very tall logging situation. And what we're seeing is, let me get my, it crashes. Where's the red? Or it crashes here. So it's like spinning on the input process. But then as soon as the output process gets execution again, it crashes then, and it always crashes when the output process gets control again. Let's take some notes. So input and output processes are fighting over the CPU. Input process is spamming in a loop. Insertion always happens when the output process gets control again. All right, but let's take a look at this. So here we have the kernel page fault, but it happens kind of differently. It's triggered by the input. I suspect there might be something really stupid. Going on here, like, but it, like, I don't know. I'm using TDT and TDD in the transmit function. I'm using RDT. This is juicy. This is a juicy problem. Okay, but so I still don't really know what's going on, but we have some more information about the source of the non-determinism. And it's pretty clear that the source is scheduling. It's some kind of scheduling issue, which is a common source of problems, or a source of non-determinism, but in one, yeah, it's like sort of about like who gets code execution first sort of thing. Output start. What again? What? So the output server is trying to send out data, right? And it just it before and after the IPC, then before and after transmit, right? Before start, before IPC, after IPC, before transmit, transmitting. So what we're seeing from these logs, the output process was running, but it got interrupted. And then the input process started just taking over and just like spamming. And then probably right here, the clock interrupt happened, and we switched and rescheduled the inputs. Yeah, and the other situation, output start. Output before and after. So after works. Before transmit. So if the output process is allowed to make enough progress, it's actually able to push out a transmit. Then the input process takes control, tries to do its first receive, and then crashes. Okay. Yes, it essentially crashes based on which child process gets scheduled. Exactly. And I don't know. Yeah, I don't know exactly how that it ends up being deterministic. It's like something to do with QEMU maybe. Because I'm only using one CPU right now for the OS. But yeah, so that's a little bit closer. So that's a little bit more information about what's going on here. So it seems like if the output process gets interrupted by input process, assert. If output process makes it through transmit before getting interrupted, page fault. So that's kind of interesting. I'm still pretty confident that I made a stupid mistake somewhere. And it would be pretty easy. Yeah, maybe I can spend a little bit more time trying to figure this out. So, but it's interesting that there's this relationship between the two actually. Maybe let's take a look at this case. Let's try to understand how this could happen. So I feel like I feel like it's even maybe a copy paste issue or something like this. Actually, I also just realized there is one other bug. I forgot to change this code. This kind of goes back to earlier when I was describing how we're going to initialize the ring buffer, and actually the simplest way to do it is just to initialize everything to be available. Yes. I don't think that would actually fix it, but no. Yeah, that's not really related. But let's mentally walk through this a little bit. See page fault. I'm more interested in this assertion right now. This is actually a nice, tight example of it. And we can kind of fairly easily reason about it. So let's imagine first we're the output process. Oh, that is actually very interesting because it was so tight. The output started, I don't know, it did the IPC receive, which, yeah, I don't know if that deschedules it. But then it switched over to the input, which did exactly like one system call. And then it switches back over to the output one and attempts to do a transmit after this has done exactly one cycle, and then it asserts. And assertion tail. Let's take a look at 296. Let's take a look at this. 296. Shit. 296. Yo, I think I know. I copied and pasted. Yeah, I'm super stupid. I used the wrong set of descriptors. I knew it was a copy and paste error. I'm in the receive call. I'm using the transmit ring buffer when I should be using the RX ring buffer. So I knew it was gonna be something so stupid, because otherwise there shouldn't really be this connection between the two. Like it was very odd that there's like this direct connection between the receive and the transmit. It was very odd that somehow the input is corrupting the state of the output, which would make the output crash. So let's run it. Oh my god. Oh yeah, I stupidly copied, so I didn't even get the types right. I was using transmit descriptors. I knew it was gonna be something so stupid like that. So that is interesting. The behavior is way different. Oops. So we successfully fixed the assertion, and now we're back. Now we only have the page fault, and that's huge progress. I'm gonna go ahead and give a bit of a victory for debugging that. Also like a huge L for me for making that awful mistake. And not being careful. But yeah, so now things get interesting though, because I think we're kind of close, actually. So now we know it's still doing a load page fault. And I think this is also fairly straightforward. I'm just doing something stupid, I think, in this function. Thanks as anything. Yeah, good point. So I'm going to, wait, I'm just going to go back to fork for this actually. So this is critical, and I'm going to, that's going to be a fix up for this. Implement basic, yes. So, all right, don't be like me, y'all. Actually pay attention to the code you're writing. It's like a win, but it's also a huge L. I think it cancels out to be like slightly on the L side. I did debug it, which is kind of interesting to debug this kind of issue with the scheduling and all sorts of stuff, but it's also such a massive L because that was such a stupid bug. Okay, so now we're back into page fault world, and this might be, did I add stream delay today? No, I don't think so. Does it sound delayed or does it seem delayed? I don't think I did, but anything's possible. How much delay does it seem like there is? All right. So page, so let's audit this code just a little bit. Tail next, like there's not actually that much code here. So is my mem copy like stupid or something? Chat delay. No, I don't think so. Should be normal chat setup. All right. So let's see if we can audit this code. Where, like, what could possibly be crashing right here? I'm actually just going to kill the palm tree because I do need to get going in a bit. So what could possibly be crashing? There's not that much code here. We read a register to find the tail. We do a very simple wrap index. Now this is interesting. That's actually, yeah, that's a problem. That's a big problem. This wrap index is hard coded to only use the number of TX descriptors. I actually don't know. TX, shit, dang. Wrap index TX. This should be RX, right? Wrap index. Yeah. So that's an issue, but I don't actually think it's a major issue because TX is way smaller anyway. But just in case that somehow made a difference, I'm going to rerun it. That did not fix it. It just, that just effectively made the ring buffer way smaller. But anyway, so we get an index, we add 1 and then wrap it to the number of descriptors, which is 128. We then index into the ring buffer at index 128. Which is of length 128. You know what? Um, I think this is this, wait, what? All right, we're gonna go way back to school here. Do I have an off by one error? Like 12? Let's say it's 16. 16, 16, 0. Um, thanks, Oz. Appreciate that. I'm trying my best. So yeah, this thing goes from, what happens if we put a 128 into this function? We're going to get a 0 out. So I think that is okay. I was just wondering if, like, is my wrapping incorrect here somehow? But no, like, yeah, if we put 128 and wrap it, we return to 0. So we wrap it till next and the tail. So these indexes are vetted. We access the pointer. Is my mem copy like in the wrong direction or something? I don't think it is. We're writing to the destination. Maybe I'll just add cprintf got data, right? So basically what's happening here is we're just looping because there's no data from the hardware, but eventually we crash because at some point we actually do get some data. So let's check out what that is. Okay, that just confirms that the crash happens when data actually finally arrives. I'm just gonna add a bunch of question marks. Where does the crash happen? Okay. The crash, like, this is gonna be so easy. That's a great stream. I couldn't learn debugging process. Yeah, appreciate that. Thanks very much for enduring my dumb mistakes. But I think it also, yeah, it shows a little bit about debugging and how I go about debugging, like, stuff. You know what? I'm just going to panic. I'm just going to panic here. And I'm just going to start commenting stuff out. Is it the mem copy? Like, I guess I should also start printing out some stuff here. Buffer len. I don't think it even gets past the mem copy. I think it's crashing in the mem copy. I've learned the hard way. Yo, I know, I don't, I think, wait a sec. I'm just gonna print all of these actually. And I'm kind of suspicious about this buffer thing. Oh, wait a sec. I think I know. I think I know what the problem is, y'all. The problem is I screwed up the permissions. Wait a sec. No, did I? Wait a sec. Wait. No. All right. I have a theory that this buffer is not writable. I'm just going to write to the first one manually, right? Wrote a single byte. I think the buffer is like not writable or something. Who passed, like, maybe I'm wrong, but yeah, no, we didn't even write a single byte. There's something wrong with this buffer. What happened here? So what is that buffer? Like, we receive this pointer buffer, but like, what is it? Who made it? What permissions does it have? The answer is here. Let's I want to, I think it might be read only. JP data. Let's see something. So JP data is this 5004 thing. That is the exact same address. Is this memory read only? The buffer in the library with the candlestick. Exactly. It seems like this greceive buffer thing is read only. Let's actually hop back to read elf. What actually, I was hoping to like find the segment that I think I'm tripping. Wait, so what I'm trying to do here is it's like, okay, my question is this buffer in read-only memory? The way I'm trying to answer that question is I'm looking at the readelf for this test input binary. I'm locating this symbol and I'm trying to find out which segment of the binary it's allocated in. And I think we can see that it's in index 4 if I'm interpreting that correctly. And I think that corresponds to the BSS, which would make sense because the BSS is for, I believe it's mutable data that's 0 initialized. I think page size. So the real question is, can we even write greceive buffer 0 equals A, right? Or does this crash? Wrote to G receive buffer. Okay. What? What? Oh, wait a sec. Okay, I don't know. That changed something. I don't know. I'm gonna remove the panic. That made things work. Syscall returned 64. Wait, check. It panics. If a syscall returns something greater than 0. Okay, I don't actually understand that, but I can easily fix this by not setting that. Okay, this thing is looping forever now. What's it printing? JP data. Crazy. Okay, so that is interesting. So this thing, so writing. Okay, I think I gotta go, guys. But here's the theory. Something about this write is paging in that page, which makes it acceptable to write from the kernel side. Without this thing, somehow that memory is not available or like paged in or something, and then the kernel crashes when it tries to access it. But if we enable this, and then yo, let's go! Oh my god, hell yes! It worked. It worked. We were supposed to see like this big ass hex dump, 542, 8,000, blah 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 blah. We see it. Yeah, let's go. Let's go. Man, okay, I don't really understand this, but we're gonna get into it next time. And a 7 on the dot. I gotta go. But yeah. Whew. Yeah, that is sick. I don't know. Yeah, I still don't really know what happened there, but we got it. So what we're just seeing here is we officially received the data. Like we sent out the ARP request. We got it back, and it actually like funneled all the way back up into user space. And it says, yeah, every time. No, it says like, yeah, you should see the hex sum of the community's ARP reply. And that stuff comes from, I don't know, somewhere else. So, yo, that was cool. Appreciate you all being here with me to help me provide the support and debug this. I'm gonna get going, but thanks very much. I'm going to link my Discord if I can find the link. Or I cannot find the link right now. I have a Discord. Whatever. I'll see you next time. Have a great week, and I'll see you next week. Peace, guys. Bye.